All right. Okay, so it's a pleasure to see some of people I know already, and it's gonna be an interesting story about geometry. I know this is more a combinatorics geometry seminar, so don't worry, this is not gonna be all optimization, but I need to motivate a little bit with the simplex method. So if you don't know what the simplex method is, don't worry, I'll remind you very quickly. Everything that I'm going to say is joint works. There's two papers that are already on the archive. So the first paper is with Alex Black, who's a graduate student here, Sean Kafer, Loera Sanita, and that you will see is a positive result in some sense about pivot rules on the simplex method. And then the main result that I'm going to talk about today is trying to understand all the pivot rules of the simplex method. Is joint work with Niklas Lutjeharms and Raman Sanyal, who are at the University of Frankfurt. Okay, so let's get started. So the motivation here is I want to solve linear programs. So what's a linear? Just so that you know, linear program is you want to minimize or maximize some linear function subject to some constraints that are linear, so linear inequalities. Yeah, so, and this, of course, everybody in this seminar knows this represents what we love, polytopes, right? So we have the set of possible solutions represents a convex polyhedron, and I'm going to assume that it's bounded. So I'm going to assume in this talk that is a polytope. And okay, so the most famous algorithm to solve this problem, and is one of the first that was popularized in applications, is the simplex algorithm or the simplex method by George Danzig, 1947. And in case you have never seen it before, so let me explain to you what the algorithm does. So you know that the feasible points, the set of possible solutions, is a polytope. And you also know that if there is an optimal solution, then one vertex, one of the zero-dimensional faces, has to be an optimal solution as well. So you start with some point. So let's say this vertex. You start with a vertex, and then you look at the edges that are going out of this vertex, and then you see, well, if there is an improving edge, you take it, and you go down. You move to another position. And if there's another edge that improves, you go down, and essentially you have this graph. The graph of the polytope is essentially, there's a walk on the graph of the polytope. It's a directed monotone path. It's going from your starting point to the optimal solution. So because these iterations continue at every moment until you reach a point where you cannot move anymore, and that means that you are at an optimal solution. So it's a walk on a directed graph, because the objective function, so you can think that the objective function in this case C is orienting the edges of the polytope, right? And one very important factor here is that you have to make a decision, right? You have to make a decision. The decision is, there might be several edges that allow you to improve. For example, in this situation, maybe this edge here or maybe this edge here, both of them give you some improvement, and you have to make a choice. And that's what we call a pivot rule, right? That's what we call a pivot rule for the, because the simplex method in reality has many simplex methods, because you have different choices, different ways you can choose the next edge. What's the best edge to choose from, okay? Okay, yeah, so you keep going with this until let's just go to the optimal. Sorry, I should have, there you are. Now you were in the optimal solution, and when you are in the optimal solution, it means, so you have no improving edges, you can stop, right? Okay, so let's but we are geometers, so this is a geometry seminar, and I'm gonna emphasize the geometry for sure. So in the simplex method again, so we have essentially, what is a linear program, if you want to think of it as geometrically, is a graph that is oriented. It's a graph of a polytope that is given an orientation that has the property that there is a unique sink on every face, okay? And so the simplex method is just selecting a good monotone path in this orientation. And again, for me, and this is going to be something very important, what is a pivot rule really? A pivot rule, well, I'm going to be very, how can I say, a little bit fussy right now. Allow me to be a little bit fussy. And I'm going to say for now, a pivot rule is just some kind of method to select the improving edge at a current vertex, right? So you have a local information, just local decision to make. And you make a decision. So let's say you're here, so you decide to go that way, right? On an improving edge. I don't want to go into a formal computer science definition of what is a pivot rule. For reasons that you will see later, I don't need it really. I will stick to some more geometric definition of a pivot rule. So you can be happy because this is geometry. I'm just thinking about monotone paths on a graph. Okay, but the big question and the reason people care, I mean, at least the reason I care for this is because it has been, more than 70 years. And this is the big question. There's $1 million, in fact, for this question solution. So you can be rich and famous at the same time. So if you want to kill two birds at the same time, you can be very happy. Yeah. So is there a pivot rule for the simplex algorithm that makes it run in polynomial, makes it a polynomial time algorithm? So it will make it run in polynomial time on the input size. So that will be number of constraints, number of variables, and the sizes of the numbers that you have. Okay, that will be already a very interesting thing to do. And unfortunately, so far we have bad news. So since 1972, we have received bad news about pivot rules. So people invent pivot rules already. Danzig, when he invented the simplex method, he invented a bunch of pivot rules. He tried to give several pivot rules, and he was always wondering, well, are they efficient, right? Are they theoretically efficient? Can I prove that my algorithm is gonna finish in a number of iterations that is polynomial or nice number of iterations, right? And I think the very first bad example is the famous Clementi Cube. So the Clementi Cube was invented by my academic grandfather. So here's my academic grandfather, Victor Klee, and here is George Minty. And so this gentleman, in 1972, they constructed this. It's a combinatorial cube. It looks like a cube, but it's deformed. And you can see the three-dimensional picture here in my slide here. So what's the story here? So the objective function goes vertically. So the optimal solution, you start here at this green point. In just one step, you should actually be able to get to the optimal solution. But when you run the simplex method with the Danzig, one of the Danzig pivot rules, that the first one that he invented, unfortunately, you get that instead of going just one step, you go two to the end steps. I mean, so you do this. You go around all the vertices of the cube before you get to the optimum. So that's bad, right? And I don't know if any of you has ever taken a class on linear programming, but in the class of linear programming, they show you this example, and they also show you that the coordinates of this cube are bad, right? Oh no, they're so horrible coordinates. So, but the reality is that's not the reason this is a bad example, because in 1973, Sade published a network simplex example. So that's just a network flow problem, essentially, where the Danzig pivot rule takes exponentially many steps to compute a mean cost flow problem. So you see, so for those of you that, I mean, in graph, so this is essentially graph theory now. I mean, there's almost no complexity on the coordinates anymore. So this is a totally unimodular system, right? So this linear program is really one of the nicest possible linear programs ever. I mean, in terms of the coordinates, but nevertheless, there's bad behavior. By the way, if you have any reactions or concerns, just let me know, okay? Just stop me at any moment. Okay. So there are so many pivot rules. Every one of you has a pivot rule with your name probably someplace, and you don't know it. You know, there's so many pivot rules that I don't even have time to go over all of them, because if I will spend my entire hour talking about pivot rules. So let me just say a few of them that are famous. So I mentioned already the Danzig pivot rule. That's normally defined in a very algebraic linear algebra way by looking at the variables in terms of a tableau for the equations. So, but there are some very nice combinatorial rules that people use. That, for example, when you are going from one vertex to another, you essentially are exchanging variables. So, because if you think about it, when you have a polytope, you know, when you have a vertex of a polytope, the vertex is defined by some facets coming together and defining that vertex, right? So that means that you have selected some hyperplanes to define that vertex, right? So when you do is you choose a new hyperplane to go to the next edge, right? So you're jumping from one hyperplane to the next, to the next, to the next. And one of the most natural rules that you can follow is the Bland's pivot rule, where you just lexicographically choose the hyperplane. So you order the hyperplanes lexicographically, and in some sense, you choose the smallest index you can in this lexicographic order, okay? And that's famous because that was the first pivot rule that in some sense, there's no possibility that you're gonna cycle on that pivot rule, that you're gonna stay in the same, you know, just going on circles. And then there's some very famous geometric rules, like the greatest improvement pivot rule. That one is just being very greedy. So you are in a vertex and you have many edges to go out of that vertex. So which one do you choose? You choose the one that gives you the largest improvement. That's very natural, right? One of the most famous ones is the steepest edge pivot rule, and that's my favorite. You will see why in a moment. Because there, instead of just choosing the one, you are very greedy, you are going to choose the one that gives you the most improvement. Don't do that. Choose the one that gives you the most improvement divided by the length of the edge. So you try to take into account whether the edge is very long. So maybe a very long edge is going to give you improvement, but that's not what you want. You want something that proportional divided by the 2 norm or by the 1 norm, the edge, the length of the edge, that gives you more improvement. So it's proportional to the length in some sense, right? So that's the steepest edge rule, and it's the most popular. When you buy software, you know, when you pay $30,000, which is really true, you can pay $30,000 to buy software to do these calculations. I mean, the commercial software that the shipping companies or, you know, United Airlines, I mean, they buy, it costs really $30,000. I'm not kidding you. So anyway, they use steepest edge. So that's why one of the reasons I really like it, because in practice, it's kind of the most popular one. So there's another one that is also very famous. If anybody from Jerusalem is here, you have the so-called random edge pivot rule, where, you know, you have all these improving edges, and you choose one at random, and that's the one that you use. Of the improving edges, you just choose one at random. And this has been analyzed by Gil Kalai, for example, and it had nice behavior, but unfortunately later people proved that it's not totally nice. There's bad examples. There's bad exponential examples, even for that pivot rule, right? Even in expectation, I'll show you the result in a moment. In expectation, it's nice, but not in general. Here's an interesting pivot rule. Sade invented a pivot rule, which is essentially keep track of what you have been doing before. Keep track of what you have been doing before. So you don't use a facet if you have used it before. So you prefer things that have not been used too much, you know. So this is called the choose the least enter non-basic variable, means that, you know, you keep track of how many times you have used that particular facet to define a vertex. And then of all the possibilities, you choose the one that has entered the list. So this one needs the history of the pivot rule to make progress. Are you with me so far? Okay, I'm gonna talk about one last pivot rule before I move to the next to my results. But this pivot rule is very important, so pay attention. And I think Karim is gonna like this one. I think it's very, very geometric. Okay, so the pivot rule that I'm interested now is called the shadow vertex pivot rule, and this is perhaps the most famous for theoreticians. So people in practice don't use this pivot rule very much. That's the truth, but it has a very nice theoretical analysis. I will say it's the most successful so far on theoretical analysis. So what is the shadow vertex pivot rule? So you start at you need to know what vertex you are in. So you are at this vertex, say. And then you have your objective function. So in this case, my objective function goes in that direction. So I have a second objective function, which is think of it as a second objective function that I'm going to use to do a two-dimensional projection. So I'm going to construct, using my objective function and this second objective function, I'm going to construct a projection from my polytope, which is maybe very high dimensional, to 2 dimensions, right? By collecting the two coordinates of the projection, I get a 2-dimensional projection, and I choose this objective function to be very generic in such a way that this vertex is the vertex where I'm standing is essentially minimized at that objective function. So I want to be sure that the shadow of this vertex is essentially a vertex on the projection, which is not necessarily the case, right? I mean, if I do a projection that is very crazy, I might get it to be in the interior, not in the boundary. Okay. So, okay, you choose this generic thing, and then you start. So when you look at the projection, so you know that you're at this initial vertex 0, and here is the optimal solution, right? Here is the optimal solution. So the optimal solution has to be on a polygon. You know, it's the projection of the objective function of the optimal solution is in the vertex of the polygon. Okay, and the nice thing is that you have just polygons are the nicest. Because they only have 2 paths, right? They only have 2 increasing paths. So you have this one on top and you have the other one on the bottom. So you only have 2 choices. And essentially the shadow vertex pivot rule follows follows a path whose shadow is exactly the top part of the polygon. Okay, that's what the shadow vertex pivot rule is. Now, doing these computations, obviously we do the computations here rather than look at the projection, because computing the projection is expensive. So we just do the computations on the original polytope. But again, it requires that phi is very generic. So this is very generic, and it's typically chosen just at random. You just choose it at random normally. Okay. Now, I think Karim is going to start seeing why I say this, but we call these paths, the paths that you obtain this way, I'm going to call them coherent, and you will see why in a moment. Now, you might be thinking, well, that sounds pretty cool, but of course, some people have found bad examples. So in other words, there are linear programs for which you can construct shadows that have exponentially many sides. So the polygons are very, very long, right? So unfortunately, that's the case. So some of the things I want to say is that we are going to modify the shadow vertex pivot rule. You will see our modification is going to make use of the non-genericity. Actually, we're actually going to rely on degeneracy. So you will see. Any questions so far? Are you with me on the pivot rules? Yeah, and so before I move to the results, So I cannot resist, because I'm speaking in this seminar in Karim's seminar, that you guys may have heard already about the famous fiber polytops, the so-called fiber polytops. So yeah, because it turns out that when you look at all possible coherent paths, you look at all of them, just all of them, there's a way to parametrize them with a polytope. So there's a polytope whose vertices are in bijection to the different coherent monotone paths. And I'm showing you one example here. So these are this is the tree cube, right? I'm taking the tree cube, and I'm showing you all the coherent monotone paths that go from this vertex to the optimum. So for example, there's this green path, or there's this green path, etc. And I'm showing you here that they have the structure of a hexagon, And in fact, the theorem that let me just put here the names of the creators of this theory is Billera and Sturmfels in 1990, when I was a graduate student, so a long time ago. They invented this. I mean, they proved that there is a polytope that is always in bijection to the monotone coherent to these monotone paths that you see in the shadow vertex pivot rule. So those are exactly the paths that you see in the shadow vertex pivot rule. And for example, if you do it in general for the n-dimensional cube, you get the permutahedron, the famous permutahedron. Here I'm showing you for the, I guess, for the 4 cube, there will be this permutahedron right here. I mean, the theory of fiber polytopes is more general, because essentially, I mean, I will tell you right away that this is obtained. The reason it's called the fiber polytope is because it's obtained by the Minkowski sum of fibers of the linear projection. So when you have a polytope and you have an objective function C, you have fibers along the projection, right? And these fibers, you take the Minkowski sum and they give you this polytope. So that's what this is. Are you with me so far? Everybody's. So I have a good reason to show you this, because my theorems, the theorems that I'm going to show you, are in some sense you can think of them as generalizations of this fiber construction. So we're going to generalize this polytope, the polytope of all coherent monotone paths, to have a polytope of all pivot rules in some sense. Okay. Everybody's happy. Everybody's having a good time, I hope. All right. Okay. So I mean, not everything is bad. Not everything in life is bad, right? So I will tell you a few positive results first, and then I tell you the classification result. So the famous thing that people know is that when you do randomly, when you look at the simplex method and you look at random behavior, for example, if Karim or Patrick just sample the polytopes from some distribution, from a specific random instances coming from some distribution, maybe the matrices come from some Gaussian distribution, etc. So then you get nice behavior. The simplex method runs in expected polynomial number of steps. But again, you're sampling your polytopes are not general, right? Your polytopes are random instances. And this idea has been explored by many people. The most famous result is by Borbar, who did a fascinating analysis. I highly recommend you read his book. It's a fascinating book where he proves that for essentially when the facets of your polytope are sampled, let's say around a spherical distribution centered at the origin, so essentially all possible directions around a sphere, then you get this nice behavior. And then Adler, Megiddo, Todd, Smale. A lot of people have looked at similar ideas, and but you are not happy, right? Because you might say, hey, my polytope doesn't come from a distribution. My polytope is very special because I'm a very special person. So I want to look at other polytopes. So I mean, there's analysis on general polytopes with random pivot rules by Kalai and Matushek, Sharir, Belsel, 1996. So for example, in the expected number of pivots that you're going to do, the steps that you're going to do is given by this amount. which is pretty good. I mean, they get a very nice analysis on this, on the number of expected pivots. But again, as I told you, that this was an upper bound, but that unfortunately is also a lower bound. So there are polytopes that take that many iterations to run in this pivot rule. And then yeah, most recently, I think this is a very hot topic in theoretical computer science. Maybe you have heard already about the smooth analysis of algorithms. So instead of analyzing the complexity from the point of view of worst case complexity, yeah, you don't want to say what's the worst that can happen. You are not a pessimist. You're not a pessimist. You want to say, okay, what if I take a polytope? You give me a bad polytope, but I'm allowed to perturb it a little bit. Just do a random perturbation. Maybe I am allowed to perturb it with a parameter sigma, right? I just jiggle the vertices or the facets of this polytope a little bit. Then I want to see what happens with your bad polytope. You gave me a bad polytope, but what happens after I do the perturbation? And see what happens with this expected behavior, right? So it turns out that Spielman and Teng and many other people, Dadouche, the latest work I guess is by Dadouche and Huberts in 2017, is that the expected diameter of the polyhedron you get is actually polynomial in the input size, and of course you need, unfortunately, you also need the perturbation parameter, right? I mean, that makes kind of sense, right? If you perturb it a little bit, maybe it's going to create a lot of, I don't know. Yeah, so it has to, it's inverse proportional to the perturbation parameter. Are you with me? So these are good results. I mean, they are positive. They tell you some good things happen if you do randomization, right? Yeah, so let me just go now to the positive results, and I will include them now. Finally, I will mention our results. So there's a big difference between the randomization that I showed you before and the results that I'm going to show you now, because these are deterministic, right? I don't want to do a randomization in any sense. I just want to look at a polytope and a linear program and run some pivot rule and get some result. So in 1997, Jim Orlin had a fantastic breakthrough, and he found a pivot rule for the network simplex algorithm. So again, these are when you have a network flow problem, you have max flow and this mean flow problems. You want to optimize the value of the flow. This can be done with the simplex method, and this can be done in polynomial time with a specific pivot rule that he found. And I'm not going to go into what it is because it's a little bit complicated. But the point is that there is at least one pivot rule that we know. And I conjecture that there will be others actually that can do the same. But there are other families that I want to show you now. So the next family is 0-1 polytopes. So this is a very important family because, of course, combinatorics uses 0-1 polytopes all the time. As you know, the traveling salesman polytopes, stable set polytopes, all the 0-1 polytopes that you can think of. I mean, for matroid polytopes or any kinds of polytopes that come from graphs, right? I mean, there's all kinds of polytopes that come from graphs. So you look at the convex hull of 0-1 points, and I don't care how you give me this polytope. I'm going to assume that you give me some linear program, but I know that my polytope is a 0-1 polytope, okay? And so here are the good news. I mean, here are our good news, and this paper is on the archive. I will tell you a little bit about how we did this in a moment. Here are the good news. The first theorem is that the steepest edge pivot rule actually takes a polynomial number of non-degenerate steps to reach the optimum. And that's good news, right? Because in some sense, the steepest edge, I told you already, is the most popular pivot rule, is the most popular way to choose the edges. Now, you have to be very careful here because I'm very careful to say non-degenerate. And I want to emphasize this for the following reason. What does it mean you know, when you have a 0, 1 polytope, is typically highly degenerate in the sense that there are vertices where the number of edges that come into the vertex is higher than the dimension, right? So, and that's bad, because when you have that situation, you might in every iteration of the simplex method, you might stay in the vertex, you might stay in the same vertex. That's what people call cycling. Okay, so 0, 1 polytopes are highly degenerate. I mean, the cube is not like that, but that's you know, pretty much just about the only 0, 1 polytope that is not like that, right? I mean, there's many. I mean, the traveling polytope, for example, the Birkhoff polytope, all of these guys are degenerate. And so when I'm very careful here, I'm saying I'm just counting how many steps, how many edges you need to improve, right? So when you really improve, sometimes you don't improve. Sometimes in some iterations, some steps of the iteration, you might stay in the same vertex, right? Okay, so that's the first theorem, and we were very happy about that.
So just to be sure,
yes.
Sorry if I made, so this theorem does not tell you something about the runtime of the simplex method with that pivot rule then, because...
Thank you very much. Yes, exactly. Okay. This theorem does not tell you. It may happen that if you run the simplex method in a computer, it's gonna take just 3 steps to get to the optimum, but to go from one step to the next, it took 10,000 million iterations, right? So that's the problem. That it might take a long time to resolve the degeneracy. And there are ways that people resolve this degeneracy that require all kinds of methods, but you see, that's not what this algorithm predicts. So what we just say is that if you are going to follow the steepest edge rule, every time you improve, or the number of steps that you need to improve is going to be polynomial. That's what we're saying. So it's more a statement about the diameter of the graph in some sense. But it's a way to do the diameter of the graph, right? Because we're following a specific type of edges, right? Specific type of edges.
Okay, thanks.
Yeah, any other questions?
Can you please explain how can you return to the same vertex?
Yeah, so yeah, let's do a little example here. So say your polytope is supposed to be 3-dimensional, just for sake of explanation, but your vertex looks like this. It has a lot of hyperplanes that give you the same vertex. So for example, because this, I can take this plane and this plane and this plane, and that gives me a vertex. The intersection of these 3 planes gives me that vertex. But I can take I can take this plane, and this plane, and that gives me the same vertex, right? So that when you implement this in the implementation, the actual implementation of the simplex method, you just jump from one set of hyperplanes to another set of hyperplanes. And you may actually end up being in the same vertex, unfortunately, because you are selecting just a switch of one hyperplane at a time, right? You switch one hyperplane each time. And, you might be choosing just a hyperplane that happens to define the same vertex. So that's the problem. So this, by the way, this does not happen if you are non-degenerate, right? So if you're like a cube, right? If you're a cube, cubes are non-degenerate because exactly every vertex is given by exactly three hyperplanes. Does that make sense to you, Sergey? Maybe you pronounce
Sergey.
Sergey. Yeah?
Kind of, but can it happen if your rule is the steepest edge rule? Because
yeah, so it can. Unfortunately, we don't know. Yeah, so the question is, can it happen with the steepest edge? We don't know. Yeah, degeneracy happens with other people's rules, so it can happen in principle. So there's no reason yet to know that. I mean, it would be nice, but we don't know.
Okay.
And also, let me say the following. So there are ways to get out of this. You don't have to get stuck for infinitely many loops, but it might take a long time before you get out of that loop. I mean, that's for sure. We know that there's some examples where you might take a long time to resolve the degeneracy, to go to the next vertex, essentially. Okay. I'm going to tell you the next result. So the next result is another pivot rule that we called the slim shadow pivot rule. Takes only n steps, and non-degenerate steps. So this is again the same thing, non-degenerate steps to reach the optimal solution. And we even have an even better pivot rule called the ordered shadow vertex pivot rule that tells you just the dimension of the polytope many, because you see the number of variables may be bigger than the dimension, right? If you have a polytope like this of dimension d, and you have n variables, right? N is the number of variables. D is typically much smaller than n. Okay. So these are pivot rules that are modifications of the shadow vertex pivot rule that I showed you before. Okay. So let me talk to you a little bit about that. Yeah. So what's the slim shadow vertex pivot rule? At least let me tell you about that. So this is a pivot rule that is a modification of the shadow vertex, and it only works. I mean, it only works nicely for 0, 1 polytopes. I'm not gonna be able to prove the same thing for general polytopes. So what I do is I'm trying to mimic the same idea of the two-dimensional projection that I did with shadow vertex, but I'm going to do it in a special way. You will see how I do it. So I started an initial vertex x0. So that's one initial vertex on my polytope. Okay. And then instead of taking a random or generic second objective function, because remember we had to choose, we had the objective function C, and then we had to choose this extra objective function B, right? I mean, we had an extra objective function. So how do I choose this second objective function to do the shadow vertex pivot rule? I take this this objective function. I take a very specific shadow. I take a very specific second objective function, which is actually highly degenerate. It's actually highly degenerate. Okay, and but essentially you still get a shadow. I mean, you still get a shadow. The difference is that the shadow is very slim, because the projection is highly degenerate. So essentially, if you think about it, this second objective function here, what is it doing? This second objective function is essentially counting how many 0, 1 coordinates you have on a vertex. So remember, all your vertices are 0, 1. I'm assuming there's a 0, 1 polytope. So when you have this second objective function, you are classifying the vertices by how many 0, 1 coordinates, how many ones are there in each coordinate. Okay, and so now how do I decide how to move to the next edge? So you have many edges, right? You are at the vertex, you're at this vertex x0, you have many edges going out. How do I choose them? Well, I mean, you have this x1, x2, etc. that you can choose to move, and then I have to choose according with this rule. So I choose, of all the possible edges, I choose the one that minimizes the slope of the C transpose divided by B transpose applied to the edge. So, and this is exactly, I'm looking essentially at the largest slope, or the edge that gives me the largest slope. And this is an edge on the polygon, actually, that will project down to the polygon under the shadow vertex pivot rule. But there are several differences with shadow vertex pivot rule. One is that this is not a degenerate, this is a degenerate projection. And the second one, that is I use the same projection for every vertex. I don't change the projection with the vertex, like in the case of shadow vertex. Here's a little example so you understand what I'm doing. And so here is I have the objective function. This is my objective function, and I'm starting at 0, 0. So here is the origin. So I'm showing you the shadow already. Here is the shadow of that three-dimensional cube. Right? Here's the shadow of the three-dimensional cube. The shadow of this three-dimensional cube is actually, I'm using exactly this projection. I'm using the projection given to me by C transpose and B transpose, right? And And the projection has, first of all, has the very important property that the number of layers, right? How many layers do I have? 1, 2, 3, 4, really corresponds to the number of coordinates that zero, yeah, the number of non-zero coordinates that I have on my vertex. So, and when I'm doing this rule of improvement, what I'm just very cleverly, if I want to improve, I have to move to a new layer, right? Every time I improve, I move to a new layer. So that's why the number of steps cannot be more than the number of layers, right? And the number of layers is bounded by the number of coordinates. So that's the idea of why this works, okay? Are you with me so far? Okay, good. Okay, so I finished this part of the talk. I'm gonna move to another. So I'm gonna continue talking about pivot rules, but this time I want to do something else. So I show you that some pivot rules can be actually nice, but I still don't know one that is nice for every polytope, right? So I need to have some kind of. So I want to find a classification of all pivot rules. I want to find a way to classify every single possible pivot rule, all right? So I want to introduce a way a very important family of pivot rules, which we gave it the name memoryless pivot rules. So memoryless pivot rules, you will see, are very, 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 very important. I argue that if you want to solve this famous question, you really need to study memoryless pivot rule. I will show you why. I will show you. I mean, our theorem is that essentially the set of all memoryless pivot rules can be parametrized by a polytope. You see, I show you the example of the fiber polytopes before. We get something like the fiber polytopes by a modification of the Billera Sturmfels construction. So you will see. So first of all, so some of you might be thinking, yo, you know, I'm a computer science person, you know, like Patrick maybe studied computer science with Emo Belsel. So, you know, so how can I define a pivot rule in the terms of computer science? And my suggestion is don't try to define pivot rules in a computer science way. There's a good reason for why you shouldn't try to do that. Because people know that pivot rules can actually encode NP-hard problems. So several people here, you know, Adler, Papadimitriou, so several people have looked at linear programs, and they said, if I have a particular pivot rule, can I answer this question? So for example, here's a very nice question. Karim gives me a linear program, and then Patrick gives me a vertex of that polytope. And here's a very, very, very simple question, very nice question. When Karim runs the simplex method, does it visit the vertex that Patrick gave me? So does it pass through my vertex? So again, you have the polytope. Here's the vertex, and you run the simplex method, and you wonder, is it gonna pass through this vertex? Right? That's the question. And the answer is, well, it's an NP-hard problem. This is an NP-hard problem for many, many pivot rules, which is kind of depressing, right? I mean, it's kind of depressing. So yeah, so no. So we, in general, you shouldn't try to, I hope you understand that if you try to make some kind of definition like that, you might run into some issues of definitions of the algorithm itself, right? The complexity is very difficult. So instead, we are geometers, right? We love geometry. And so we are going to use geometry to do a formalization of what it means to be a pivot rule. What really means to be a pivot rule for geometry. So I'm going to define a geometric object that I hope you guys are going to like a lot. And that is the footprint of a pivot rule. So what is that? So you start with a pivot rule, with a linear program and a pivot rule. So you have the pivot rule gamma, and the linear program given by P, the polytope P, and an objective function C. So remember, you already have a directed graph, right? You already have a directed graph, and at every vertex you can choose an edge, right? Like in every vertex you can choose an edge. So in fact, you can choose, for every vertex, you can choose the path that goes to the optimal solution, right? So I'm going the footprint is the subgraph that you obtain as the union of all possible paths from every vertex, starting from every vertex. So you get a graph, a subgraph of the entire graph of the polytope, right? Are you with me? So the definition is very simple, right? Now, I can give you the most important definition of the rest of my talk in the last few minutes. I have like what, 15 minutes, 10 minutes, 12 minutes, something like that, right? A memoryless pivot rule is one where the graph that you get is an arborescence, it's a directed spanning tree. You know, an arborescence is a directed tree that has a unique root, and the root is the optimum. Okay. So I will show you some examples of things that are so the footprint, again, is the subgraph that you get by looking at all possible paths. You collect all possible paths that you can have. And then the memoryless ones are the ones that you actually get spanning trees. Okay, let's look at some examples. Yeah, so, okay, yeah, there's an equivalent way to define memoryless pivot rules, and that's that when you are at a vertex, you only depend on the current information. You don't need the historical information to figure out what's the next vertex, right? And so there are examples of things that are naturally pivot rules that are memoryless. And this is, for example, greatest improvement, the one that you just maximize, you know, greedily. That's one. The steepest edge is another one that is memoryless because you only need the local information to do the decision. So examples that are not memoryless, I already told you the Shadé's pivot rule uses the history. And in fact, shadow vertex pivot rule, if you implemented the way that people define it, because you define the projection in a unique way, then you are actually not able to, you know, you might actually have to you might revisit a vertex several times. So you might do something like this. You go on a path like that. If you start with this vertex, you go on this path, but if you start here, you go in this different path. So you create cycles if you do that. Because again, in the way that people implemented shadow vertex rule, in some sense, they started the projection with every vertex, right? We don't do that anymore. We want to modify our modifications of the shadow vertex pivot rule. Don't restart the projection with every vertex. We just stick to the same to one projection, and that's it. Okay, here are some arborescence. Yeah, so when you have the memoryless pivot rule, you have arborescences only like that, and yeah. You might be saying, well, why are memoryless important? Well, remember that we want to find whether there is the big open question that is going to make you rich and famous says that you want to find a pivot rule that the number of steps is polynomial, right? The number of steps is polynomial. So that means that the shortest path on that tree, on that subgraph has to be polynomial. But I claim that, you know, maybe Patrick gives me a pivot rule and it's not memoryless. Okay, no worries, because I can take the footprint of Patrick. You know, I take the footprint, and I can compute the tree or shortest path in the footprint of Patrick, right? That gives me an arborescence. That gives me an arborescence, and this arborescence is. I can interpret it as a new pivot rule. Every arborescence gives me a pivot rule because it tells me how to go to the next vertex, right? So in other words, from every footprint of any pivot rule, I can get a memoryless pivot rule, which is going to have diameter shorter, or at least, you know, it's going to be less than or equal than the original diameter that I have, because I use the shortest paths. Are you with me? So that's a very important reason why we care about memoryless pivot rule. And in the remaining time, I will show you that in fact, memoryless pivot rules are a polytope. Surprisingly, they are really a polytope.
So I have a short question, if I may. So if I get this correctly, then there must be good memoryless pivot rules, right? Because you could just start at the optimum, do some breadth first search, take the spanning tree that you get that way, and that would define a memoryless pivot rule.
No, it's not that easy because
Yeah, I mean, it's a,
I mean, it would not be
it's kind of
computable
cheating, right?
efficiently,
It's
right?
more,
Yeah, that's why I'm asking.
memoryless pivot rule, but it's kind of, can be a computational nightmare.
Yeah,
to get, right?
but since we're ignoring computation of those things,
right.
this
No,
in theory exists, right?
So okay. So first of all, the size of the graph, you know, can be exponential simply because of the number of vertices, right? Sure. So the computation of the actual thing itself is yeah. I'm not. Yes, you're right. I'm ignoring the computation, the cost of computing this thing. So is there one? You're asking whether there's one efficient, right? Mm-hmm. Well, I will have to see whether all the shortest paths are bounded, right? In terms of a polynomial.
Right.
And that I don't know yet. Mm-hmm. Yeah.
Okay. Yeah. Right.
But yeah, again, we are not. I'm trying to avoid the kind of the complexity and the decision problems that are behind many of these things by just looking at what will the graphs. What will these footprints look like? Okay, so I'm going to define as a family of pivot rules called the normalized weight pivot rules, which you will see they are essentially the shadow vertex pivot rule or the slim shadow that I showed you before for every polytope. These are done for every polytope, and they are going to turn out to be very nice memoryless pivot rules. Okay. So how do I define these new pivot rules? So I have a polytope and I have my objective function as usual. Okay. And I have a weight. I call it B before, but we can call it yeah. Anyways, you have an extra objective function. And you have also a normalization, which you can think of as the 2 norm or the LP norm of the edges. So how do I choose the next edge? So my vertex is here, right? I have my vertex, what is it? Let's say U, and then I have all these neighbors. I have to choose all these neighbors. So I have to choose the neighbor that maximizes the quotient, the ratio between the value of improvement in the direction of W and the normalization. So you can think that the normalization is giving you some kind of ball. You have some ball that shrinks the sizes of these edges, right? You have some normalization. Again, you can think of it as a norm, like the two norm, and you divide the improvement by the normalization. So this is, you can think of it when this is a norm. This is essentially a steepest edge version, but the normalization might be crazy, might be another crazy function, not necessarily a norm. And in fact, one of my favorite ways to normalize is maybe I just divide by another objective function, by a third objective function, right? So anyway, so that's the way I choose the improving in every neighbor. So I'm going to say that this is the normalized weight pivot rule. And of course, there's many examples of NW pivot rules, right? I call them this NW. Oops, sorry. Yeah, so here are some examples that are very nice. So the greatest improvement, for example, is just you don't care about the normalization. You just look at the longest edge if you have to, right? You just don't normalize the edges. And the W will be just the same objective function. I mean, you're just using the same objective function. For example, for steepest edge, you take the objective function and then you take the norm, the LP norm. So several people have looked at this in Japan, the Japanese mathematicians, Kitahara and collaborators. And then one of the most beautiful ones, in my opinion, is you take the normalization you use is the objective function. And then you pick your W to be generic. It's essentially relate to the max to the shadow vertex. You pick W generic perpendicular to your objective function. And in some sense, this is a memoryless generalization of the shadow vertex pivot rule. So see, the difference with the shadow vertex pivot rule is that we stick to the same projection for every vertex. I just want to remind you of that, right? Okay, so every memoryless pivot rule, sorry, every NW rule is a memoryless pivot rule by almost by definition, right? But you might say, Jesus, is every memoryless pivot rule an NW rule? And the answer is no. Here's an example, actually, with a regular 3 cube. So the reason this is not memoryless in this embedding is because, sorry, the reason this is not NW is because in NW, when you are at a vertex, and if the cone of the vertex, so for example, here is this vertex here. Let me see. I think. Oh, sorry. Here is the best picture. So if you look at this, when you're at a vertex, you need to be consistent on the choices. If the tangent cones look the same, so look at these two vertices. The tangent cones are essentially orthons, right? And if the orthons are identical, you should somehow expect that you make a consistent choice, because yeah, that's the way we run it. Okay, by just looking at the adjacent vertices, right? Adjacent vertices. So, but here it's not a consistent choice with respect to the adjacent vertices. In this case, it goes down, and here it goes up, right? Okay, so that's bad news, because not every memoryless pivot rule is NW rule, but almost. Let me tell you what I mean by that. So we prove that if you have a polytope, the memoryless pivot rules may not coincide with the NW rules, but you can perturb it and it will happen. So this is the case when all the edge directions of your polytope are different. And there's always a perturbation of your polytope that preserves the combinatorial type that gives you this property. The edge directions are different, and when the edge directions are different, then the cones will not have this coincidence that we had before. So you can be consistent on all the choices with the NW rules. Okay, so you can choose actually a weight, and you can choose a normalization, and you can do this. Now the way that you choose is going to be very easy, but the normalization is complicated. So in some sense, see, that's why we want to study these polytopes, because that's why we want to study the NW rules, because NW rules in some sense characterize the memoryless pivot rules as long as your polytope has a very specific embedding, right? Yeah. So finally, because I'm running out of time, let me get to the final theorem. So when you let the 3 parameters, you have 3 parameters, CW and CW and the normalization, and you let them change, you're gonna get a polytope that parametrizes all possible outcomes, all the possible arborescences that you're gonna have with these pivot rules. So yeah, so let's just get to the punchline. So if you change the weight and you fix the objective function, you have a linear program and a normalization, and now you let the other weight change in many different ways. What you get, let me just get to the theorem because I'm running out of time, is that there is a polytope that we call the pivot rule. So that should be the pivot rule polytope that actually the vertices correspond to the different arborescences that you can obtain from the NW rules, And yeah, so that's what we constructed. And just because I'm running out of time, let me tell the construction is exactly a variation of the fiber polytope construction by taking Minkowski sums. But this time we don't take Minkowski sums of the fibers of the projection. Just we look at the fibers around vertices, only around vertices, and we restrict to the hyperplane of the vertices, essentially, generated by the increasing edges of the vertices. So it's a slight modification, but it comes inspired from the fiber polytope construction. All right, so I ran out of time and I hate people going over time. So I'm going to stop here. Thank you very much for your patience and I'm ready for your questions.
All right. Thank you very much, Jesus, for the really nice talk. I mean, if there's more that you wanted to say, I guess feel free to after the questions if people are interested. But in the meantime, are there any questions from the audience?
Is there a universality theorem for these for bad polytopes? So let's say I give you some kind of a pivot rule given under some kind of in some kind of class. Can I always find a polytope that takes exponential or linear program that takes exponential time?
So, okay.
I mean, somehow there's of course there's people that construct for every given one. But that's not what I want.
Right. So essentially,
I want to be lazy.
Yes, I agree with you. Okay. The answer is no. We would love to find that. That's exactly what we are going for, right? So we want one family of LPs. We want a single family of LPs that is bad, really bad for every pivot rule, right? At least, as you saw, what we want to prove is
no,
that.
But I don't want to. Yeah. Okay. I want to.
Yeah, we want a family of LPs that is bad for all memoryless pivot rules, for all the NW rules that I just presented, for example. That will be the end of it, right? That will be essentially finished. Now,
but I mean, we know. I mean, there is no deterministic one that reaches the Calais sub-exponential bound, right?
That is correct. That is correct.
So is it known? I mean, that would be the interesting question, right? There is some small. I mean, in the end, you want to say, I mean, you want to prove that there is no determinant, or that let's say in your class of memoryless, there's no deterministic one, or I don't know.
Yeah. So one thing that I can tell you is that if you look at the footprint of the random pivot rules that Calais has, those are not memoryless, right? I mean, because
of course not. Of course not.
Yeah, they're not memoryless. But so here is one thing. Every pivot rule that we know today, 2022, we have a bad example, but it's a different LP. It's a different family of LPs for every pivot rule. So we would like to have some, as you said, some kind of universal linear program, like the most ugly linear program ever, right? That actually has this property. Now, you mentioned something very important, actually, that so there are these exponential examples for the Calais pivot rules. So do we know anything about those, the memoryless pivot rules for those polytopes? No, we don't. I mean, those are some deformed cubes, actually. Those are deformed cubes that we should look into that. We haven't had a chance to do that yet, but that's a very interesting direction. And why? Because they are bad for the randomized problems, right? So hopefully that means something for the deterministic cases, right? Yeah, absolutely. Yeah. So any other question?
Are there any other questions?
If you don't have another question, I'm going to show you just one more thing that I think maybe you guys will like. If I take, the normalized pivot rule, sorry, the pivot rule polytope so I get some nice combinatorics. This might actually get some of you excited. I don't know if some of you may like the associahedron and the permutahedron, all this. So the pivot rule polytopes for some easy linear programs, they're actually cube. I mean, like the cube or the simplex, you actually get the associahedron back and you get the permutahedron. So it's very reminiscent to the secondary polytopes, right? You get these nice constructions back. And another thing that is nice is that, so it turns out that the monotone path polytopes that I show you at the beginning, they are actually Minkowski summands of some of these pivot rule polytopes, or the pivot rule polytopes that come from the max slope choices. When you have sonotopes, then the monotone path polytope and the pivot rule polytope coincide; they become the same. So the connections to fiber polytopes are very strong.
Sorry, I have a question. Can you go up again to the last slide? Yeah, that with the examples. So there you say that for certain pivot rules, you get special polytopes.
Yeah, so it's nice. There's nice combinatorics. It's not just optimization results or polytope results. I mean, if you care about algebraic combinatorics, you know, or some combinatorial objects, you get some. So you recover some of the classical people construct polytopes, you know, by using combinatorics. Like a sociahedron is related to, you know, spanning trees or, you know, binary trees, and the permutahedron is related to permutations, and you have triangulations related to this. So you recover some of these by these constructions. Actually, some of these pivot rule polytopes are actually nice combinatorially.
Okay.
So
cool. Nice. Are there any other questions? That does not seem to be the case. So thank you again, Jesus.
Thank you very much.
And for the answers, and I will stop the recording now.